All right, so let's think about these practice problems and I'm going to help you understand how to think about them, how to do them. In this particular practice problem, there is a car, 875 kilogram car. That's the mass of the car. It's speeding up from 22 meters per second to 44 meters per second to pass another car. And they want to know how much work is done by the car to do this. All right, so several things to notice. First, they give you the mass. Second of all, they give you an initial speed and a final speed, two speeds. So to draw a very simple picture, it's really useful to do this with all of these problems. Just draw a very simple picture. This car is speeding up from 22 to 44. I want to label a couple of things on this picture. First of all, this is my initial energy state. That's my final energy state. And it's important that in each problem you decide that you know what kind of energy is going on at these places, at these times. And these are our three choices, potential, kinetic, or neither. So at the beginning, the car is moving. Remember, and back up, potential relates to height. Kinetic relates to speed. This problem is all about speed. There's no height in this, so potential energy is not going to come in at all. As a matter of fact, we have kinetic energy in both locations because it's just moving in both locations. There's a higher amount of kinetic energy here because the car is going faster. It goes from 22 to 44 meters per second, so it's increasing its kinetic energy because it's increasing its speed. But we want to know how much work is being done here. So, first thing is when you see the word work, you need to write down this whole equation. But remember, we don't have to write this part down. We don't really have to write down the delta E because delta E is EF minus EI. So I'm just going to write down W equals EF minus EI equals FD. It's a three-part equation. We only need two parts. So we're going to pick those two parts. They want work. I got to have that. So now we either get rid of EF minus EI or FD. I'm going to get rid of FD because they neither give me the force or ask for it, and they don't give me the distance or ask for it either. So I'm going to get rid of that, and for this particular problem, that's going to be my equation. Remember, really important here, when you're doing EF minus EI, you have to know what kind of energy it is. One of the most common mistakes is people put a speed in here. They'll put 22 right here, they'll put 44 right here. The speed helps us to calculate the energy, but the speed is not the same thing as the energy, and neither is the height if we were given the height. So we can't just put those numbers in here. We have to remember that we have kinetic energy at both locations, and what we're going to put in the next line is the kinetic energy formula. You might remember that it's mv squared over 2. mv squared over 2. And since this is final, I'm going to put an F right there for final speed to tell myself that I'm going to use the final speed for that. And the same thing for the initial energy. It's also going to be mv squared over 2 because they're kinetic energy at both locations. But this one's going to be different because I'm going to use the initial speed to calculate it instead of the final speed. Zoom in on that a little bit. All right, so we're going to plug in some numbers and do some calculations here. W equals, the mass is 875. The final speed is 44. Don't forget to square that over 2. Minus, and I know I'm kind of getting all over myself, on top of myself right here. 800 and, put the 2 right there. 875 times 22 squared, that's our initial speed, over 2. And when we do this, we have to do these separately. It's basically calculating the final energy, calculating the initial energy, and we're going to get two numbers and then subtract them. So if you do all this, we're going to do, remember we have to do the squared first, 44 squared times 875 divided by 2, 22 squared times 875 divided by 2. Do those real fast, pause the video. If you do that, for the final energy, you get 847,000. And for the initial energy, you get 211,750. 211,750. Somebody sent me an email. And if you subtract them, you get 635,250 joules. The engine did 635,250 joules of work in order to speed this car up. In other words, in terms of our bank account, bring my bank back, the engine, well, we started out with $211,750. We already had $211,750 in the bank. The engine did work to deposit $635,750 more dollars into the bank, and therefore we ended up with a final balance of $847,000. That's what happened here. Instead of dollars, we're talking about energy. So all that happened here is we started out with $211,750. The engine does this much work, and you end up with that much energy at the end. All right. The second scenario says once up to speed, that means the speed of 44 meters per second. How much work does it now take the car to stop? So to be clear, we want to understand that this car is not doing the same scenario now. Now instead of going from 22 to 44, now we're going to go from 44 to 0. All right, so here's my initial energy. That's kinetic energy because the car is moving, still no height involved. And now we're stopped. At the end, EF, we're stopped. Therefore, there's no kinetic energy, still no potential energy. So the energy is 0. There's nothing. There's no mechanical energy that the car has here. All right, so we're looking for work. I'm going to write down the whole equation again. W equals, pen is broken. You see that? Somebody broke my pen. Maybe you've already seen that. I just saw it. Anyway, y'all don't want to go with my ramblings. You don't want to hear that. W equals EF minus EI equals FD. Same thing as before. We're going to pick two parts. Same thing as before. We're going to get rid of FD, although that won't always be the case, simply because they don't ask for or give us force or distance. We're going with this. The final energy is 0. We're going to put a 0 in here. The initial energy is kinetic energy. So we're going to put the kinetic energy formula in here. So our next line is going to say 0 minus mv squared over 2. Write the rest right here. 0 minus the mass. The mass is the same car, by the way, if you hadn't caught that up to this point. 875. The speed is now 44. We're starting at a 44 meters per second speed. Over 2. And you don't have to calculate this. The reason is because we just did it right there. And we got 847,000. So in order to stop this car, 0 minus 847,000 gives us negative 847,000 joules. And the question is it okay that we got a negative? Is it okay that we got a negative? And the answer is yes. Energy can never, ever be negative for the same reason that, hopefully, the money in the bank is not negative. It's negative if you overdraw, but let's just imagine that that's not happening right now. You always got a positive amount of money in the bank, but deposits and withdrawals show up on your statement as positives and negative because when you're withdrawing, you're taking money out. So a negative for work is possible because it means we're removing energy from the system. In other words, it means that that should be an R, energy was quote-unquote lost. Now, I put the quotes in there because remember, the law of conservation of energy says that energy can neither be created nor destroyed. This energy is not destroyed. We have 0 energy here at the end. It doesn't get destroyed. It goes somewhere, but it is lost from our system. It goes away from the car. Let's talk about where that energy goes. So, to begin with, we started at 22 meters per second. We went to 44 meters per second. All right? That was our first scenario. In the second scenario, we went from 44 to 0. We were stopped. I want to talk about the energy transformation again. I want to trace the kinds of energy that we have. Well, the car had kinetic energy here while it's moving. It's got kinetic energy here. The kinetic energy is increasing while it's speeding up. We still have kinetic energy right here. But the question is, what was the energy or where was the energy before it was kinetic energy? Well, the way you get your car to move is you hit the gas. And the energy before it was kinetic energy was in the gas. It was in the form of chemical energy in the gas tank. right? So the gas gets sent to the engine, right? In the engine, what happens to the gas? Well, there's tiny explosions that go on. Those explosions create heat. So from the chemical energy in the gas, we get heat energy inside the engine. That's why your engine is hot. Move that arrow because it looks confusing now. The heat causes air to expand. So we have all these air molecules that are rapidly expanding in the engine, and that expansion creates the kinetic energy in the piston in the engine. The piston in the engine causes the car's wheels to move, and therefore the whole car moves. So we get chemical energy getting transformed into heat energy in the engine. That heat energy became kinetic energy as the car moves, but now we have zero energy. Where did the energy go? The answer is it goes somewhere. It goes somewhere, and we'll talk about where that energy goes in just a moment. Before we talk about that, let's go a little bit faster and talk about this problem with the rifle shooting a bullet. First thing we need to know about this bullet is we don't like masses in grams. We need to change it to kilograms, which is 0.005 kilograms. Shoots a bullet at a speed of 400 meters per second. How much work is done on the bullet if it starts from rest? So once again, if we draw a picture, the bullet's moving at 400 meters per second. At the end, that's kinetic energy because it's movement. There's no height involved. At the beginning, the bullet's at rest. Therefore, the initial energy state is just a zero. There's no potential energy. There's no kinetic energy. We want to know how much work is being done. So I'm going to write down W equals EF minus EI equals FD. Same process as before. We're going to choose the two parts. And just as before, we're not given or asked for force and distance. So we're going to use this. Final energy being kinetic, initial energy being zero. So on this one, I'm going to say mv squared over 2 because it's kinetic energy at the end. Initial energy is 0, starts from 0. The mass is 0.005. The speed of the bullet at the end is 400 over 2. If you do that math, minus 0 doesn't change anything, but we're going to throw it in there anyway. But if you do all that, you will get 400 joules of work that's done on that bullet. It does 400 joules of work. Now, this is like, it looks more complicated than it is because basically all we did is we calculated the kinetic energy of the bullet. That's all we did. Like, we'd get the same answer if I said, how much kinetic energy does the bullet have? Well, that's a really easy question, just mv squared over 2. But that's all we're doing. So again, bank account, how much money did you have right here? Well, you had nothing. How much money did you have here? Well, we had 400 joules. That's all we're doing is how much money was put into the bank. If you have $400 at the end, you had to put $400 in. That's all we're saying here. The next question, it says this work is done over a distance of 0.75 meters. That's our distance. And we want to know the force. Force is what we want. So this one's going to be slightly different. Still going to start with this because it's safe. But in this one, I'm actually not going to do EF minus EI. It's going to be much easier to do W equals FD, like the old school way we did it, because we just calculated the work up here. So I'm going to put that in. 400 equals force times the distance of 0.75. That's basically saying the length of the barrel is 0.75 meters. That's how long the force was exerted on that bullet. To solve this, you'll divide by the 0.75, and that tells us that the force, 400 divided by 0.75, is 533.3 newtons.